Okay, let's dive into this. Welcome to The Explainer. Today we're looking at what is honestly a massive paradigm shift in our understanding of reality. Have you ever stopped to wonder if maybe the biggest mysteries of the universe aren't actually missing substances, but just misunderstood geometry? Well, we're unpacking a framework called mode identity theory, and it completely reimagines what we currently call dark energy and dark matter. This isn't just some minor tweak to standard cosmology either. It's a fundamental rereading of the universe's baseline structure. We're going to look at how a surprisingly simple boundary condition might actually solve the single largest discrepancy in the history of physics. And when I say largest discrepancy, I literally mean the worst prediction in all of physics. Just look at this number. 10 to the power of 122. That is a 1 followed by 122 zeros. In standard physics, when you use quantum field theory to estimate the vacuum energy of the universe, looking at zero-point fluctuations, and then you compare that to the actual observed cosmological constant, the theory is off by this staggering, unimaginable amount. For decades now, physicists have been banging their heads against the wall trying to figure out why the cosmological constant is so vanishingly small compared to those quantum predictions. Which naturally brings us to Albert Einstein. Back in 1917, Einstein famously added the cosmological constant, that's represented by the Greek letter lambda, to his field equations, mostly because he wanted to hold the universe static. But later on, when Edwin Hubble observed what sure looked like the expansion of the universe, Einstein took lambda out, reportedly calling it his biggest blunder. But here is the incredible double take from the source material we're digging into today. Einstein was actually right the first time, just for reasons he couldn't have possibly known back then. The framework we're exploring suggests the blunder wasn't adding lambda. The blunder was actually taking it away. So let's draw a really sharp contrast here. Standard cosmology revived lambda about a century later, calling it dark energy, this mysterious, expanding fluid that's supposedly pushing the universe apart. But the mode identity theory perspective, it argues there is no dark energy, no mysterious fluid, none of that. Instead, it proposes the universe is a finite, static three-sphere. What we've been perceiving as an expanding spatial universe is actually a static geometry governed by a standing wave on a cosmic boundary. So it's not a dynamical fluid at all. It's a fixed geometric reality.
Act 2, the ground tone.
To really wrap our heads around this, I want you to think of the universe not as some expanding balloon, but like a musical instrument. And just like a guitar or a flute, a bounded geometry only permits certain resonant frequencies, right? It has a fundamental ground tone. In this view, the cosmological constant isn't just some random parameter dialed into an equation. It's the ground mode eigenvalue of the cosmic boundary itself. The geometry of the universe essentially acts like a cavity that constrains vibration. And this is where it gets absolutely fascinating. Why does lambda have its specific, constant value? Well, because it sits perfectly protected at what's called a topological antinode. Notice how at an antinode, the slope is exactly zero. Since the logarithmic slope of the mode spectrum is zero there, any random environmental perturbations leave it completely unmoved. You literally cannot perturb your way out of a topological node. So, the cosmological constant is locked in place. It's topologically protected.
And here you can see the structural rules that actually lock that ground state in. The universe's boundary imposes an anti-periodic boundary condition. Now that simply means that traversing the boundary once flips the sign of the field, so it takes a period of 4 pi or 2 full traverses to restore it to its original state. Plus, the cosmos selects the ground state without higher harmonics. Why is that important? Because higher harmonics would create internal nodes in observable anisotropy. But we know from measurements of the cosmic microwave background that the universe is highly isotropic. It looks the same in all directions. This selection rule structurally guarantees that lambda sits right there at that foundational baseline. So, you're probably wondering, what on earth is the shape of this boundary that imposes these rules? Well, the source material gets into some truly mind-bending geometry here. The cosmic boundary is described as a curved, non-orientable Mobius surface. Specifically, it's a Mobius band embedded within a three-sphere. Think about that. The boundary has a single, closed loop traversing the band twice. It's exactly this twisted geometry that forces that anti-periodic boundary condition we just talked about. Traversing the band once brings you to the flip side, which imposes that sign flip natively, purely through geometry alone. Now, when you do the math to measure this twisted curvature, specifically using the Laplace-Beltrami operator on this curved Mobius surface, the math returns an exact topological eigenvalue. And that value is 2 divided by r squared, where r is the curvature radius of the cosmic three-sphere. The crazy part? This isn't just an approximation. The calculation shows that this ground eigenvalue perfectly equals the exact scalar curvature of the surface itself. It's a pure geometric output based entirely on the boundary condition of that Mobius topology. Act 3. The 3-2 interface. Okay, but now we have a bit of a puzzle. We just defined a topological eigenvalue on a two-dimensional surface boundary. But you and I, we don't live in 2D. We experience a 3D spatial reality. So how exactly do we bridge this mathematical gap? That's the crucial question we need to ask. How do we experience a 2D topological surface in our 3D reality? General relativity doesn't read the surface directly. It reads the 3D space. So we need a translation layer. We need to know the exchange rate, basically, between the two-dimensional boundary surface and the three-dimensional ambient space where we actually observe things happening. Thankfully, we can bridge this gap using classical differential geometry, specifically a tool called the Gauss equation. It's a three-step process. Step 1, we start with our intrinsic 2D surface curvature. Step 2, we relate it to the curvature of the 3D isotropic ambient space it's embedded within. And step 3, we apply the conversion. The Gauss equation effortlessly translates this intrinsic surface geometry right into observable ambient space curvature. It effectively does all the heavy lifting to bridge that dimensional gap for us. And the result of that Gauss equation conversion, it's exactly this ratio, 3/2. This is the vital interface. The 3 reflects the three-dimensionality of our isotropic space, and the 2 comes from how general relativity algebraically defines lambda. So that 3/2 ratio is the exact cost of carrying information from the 2D cosmic boundary right into our 3D spatial dynamics. It's like the fundamental time signature of the universe's geometry. So the absolutely crucial point here is this final elegant output. If we take our 2D surface eigenvalue from earlier, remember, that was 2/r², and we multiply it by our 3/2 interface conversion, well, the 2's just cancel right out, and we are left with lambda observed equals 3/r². Boom. The observed cosmological constant isn't some random parameter arbitrarily dialed in to fix a broken expanding fluid model. No way. It is a fixed geometric reality derived directly from the topology of the universe. That massive 122 order of magnitude discrepancy completely vanishes because we stopped mistakenly equating a geometric boundary condition with local quantum zero-point energy. They were literally never the same thing to begin with. Now, just to be thorough, for this math to hold up, it does rely on 3 strict conditions to validate that Gauss equation conversion. First, it requires a totally geodesic embedding, meaning the ground state carries no extrinsic structure. Second, the space has to be isotropic, and the good news is that's beautifully verified to a factor of 10 to the -5 by our measurements of the cosmic microwave background. And third, it requires a de Sitter vacuum, which actually aligns perfectly with the late-time attractor in standard cosmology. Because our observable universe meets all these conditions, the geometric math stays completely grounded in reality. The ultimate test. As we all know, a brilliant mathematical theory is only as good as its hard falsification. And this static space framework is actually putting its money where its mouth is, with pre-registered falsification criteria waiting for the 2026 Euclid Space Telescope data release. For instance, if the standard Mond acceleration scale A0 does not evolve with the Hubble rate at high redshift, this theory is totally dead. If lambda is shown to actually vary with redshift, like a dynamical dark energy fluid would, the theory is dead. And finally, because dark matter in this framework is purely a geometric effect of the 3D space, if a non-gravitational dark matter particle signal is ever definitively found, this entire framework is falsified. It is an incredibly bold, confident, and testable stance. Which leaves us with this truly profound metaphor to end on. Einstein's field equations are the score. 3/2 is the time signature. The universe isn't filled with some phantom dark fluid pushing space apart. It might just be an elegant, unchanging geometry playing a fundamental resonant tone, where what evolves isn't the universe itself, but our perspective moving along the wave. It's a beautiful thought, isn't it? Could the absolute greatest mysteries in cosmology just be a matter of reading the geometry correctly? Thank you so much for joining me on this deep dive into the explainer. I really hope it left you with as much to think about as it did me. So, what do you think? Keep questioning, and I'll see you next time.